Now that we're done with using convolution sum as a tool to compute for the output of an LTI system uh, to an arbitrary input sequence, and that we have used the impulse response um, to be able to determine that output sequence. We will now use the impulse response to identify or to characterize the system, okay, or the LTI system in terms of its other behavior, or its other behavior. Okay, so in this lesson we will revisit two characteristics that we have discussed before, but we have discussed them in general terms. Okay, and that is the causality of the system as well as the stability of the system. Okay, we will revisit them now. Okay, but in view of the impulse response as a way to determine the system's causality and uh, stability. So in lesson 2.4, various characteristics of discrete time systems represented. Okay, so we have zeroed in on starting lesson 3.1. We have zeroed in on a class of discrete time systems that are considered linear and time invariant. So we we call it LTI system. Okay, so not only that it is mathematically convenient, the analysis of LTI systems also applies to most practical systems. Okay, either they are algorithms or they are circuits. So effort is not lost in the study of LTI systems. In every study of signal systems that you will encounter, you will really start on what we call linear and time invariant systems, because that's where everything actually starts. Okay, so again, in lesson 3.1, we have used the impulse response of a system as one of its representation. Okay, so remember that we have two representation as of now. We have two representations, or your system can be represented in two ways. Okay, so in general, every system, regardless if it is LTI or not non-LTI, we can represent it using input-output relations. Okay, while specifically, um, relaxed um, relaxed LTI system, okay, can be represented by what we call the impulse response. Okay, that is the sequence generated by that system to a unit sample sequence input. So why are we motivated by this choice of representation? Um, Aside from allowing us to compute the output sequence produced by the system to an arbitrary input sequence, and we do that via the convolution sum, that is our previous lesson. Okay. The impulse response of the system somewhat characterizes the systems in other ways, aside from letting us compute the output of the system. Okay. Now, these characteristics as it relates to the impulse response are discussed in this lesson. So, as I mentioned earlier, some of the characteristics that we will be mentioning here have been discussed in lesson 2.4. Uh, that includes two, causality and stability. Um, these characteristics are given new attention considering the new information that is the impulse response. However, some characteristics are unique to LTI systems. So, since we're talking about, or we are in on the discussion of LTI systems, we will be also talking about characteristics that are unique to LTI systems only. Okay, and see how the impulse response can actually be used to define these characteristics. Okay, now let's discuss causal linear time invariant system. Okay. So in the previous topic, that's lesson 2.4, a causal system, okay, was defined as the one whose output at time n depends only on present and past inputs. but does that depend on future inputs? Okay. It also includes in hindsight, it also includes past outputs. Okay, and it doesn't depend on future outputs. Okay, so in the case of LTI systems, causality can be translated to a condition on the impulse response. Okay, and that is an LTI system is causal if and only if its impulse response is zero for negative values of n, or your h of n is zero when n is less than zero, or when n is negative. Okay, so that is how we will say, or that is how the um, impulse response would look like for a um, causal LTI system. Okay, so now, so here, we remember that we have classified our system, or our actually this figure, okay, um, illustrates sequences, okay. Pero if these sequences are actually impulse response sequences, then they can also be used to describe systems. Okay? So, ang nakita nyo dito sa figure na to ay sequences. Okay? For example, this one is a causal sequence. Okay? So, as you can notice, the values of the causal sequence when n is negative, okay? When n is negative is 0 and non-zero siya, okay? When n is greater than or equal to 0. Okay? So that is what we call a causal sequence. Okay? But if this sequence is actually an impulse response sequence, okay, then this is how the impulse response looks like for a causal LTI system. Okay? So tawag nga natin dito is this is a right-sided sequence for obvious reasons. Okay? Now, we also have anti-causal system, anti-causal sequence, okay, in which an anti-causal sequence is non-zero, okay? It's non-zero for negative n, okay, and 0 for positive n. Okay? So that is an anti-causal sequence. But again, if this pertains, or if this sequence is actually an HN or an impulse response sequence, then this describes a system, okay, or this is the impulse response sequence of a system that is called anti-causal system. Okay? We also call this sequence, okay, a left-sided sequence. Okay? Now, this sequence is two-sided. As you can see, it is non-zero for all. Okay, there are non-zero there are non-zero values of your sequence for negative values of n and positive values of n. So this is called a two-sided sequence, or a non-causal sequence. Okay, and if this describes an HN or an impulse response sequence, okay, then the system described by this kind of impulse response is classified as a non-causal system. Okay, so we have causal, anti-causal, and non-causal. Okay, now going back yet, the causality condition for LTI system, okay, if we now apply, okay, the causality condition for LTI system to the convolution formula, okay, and that means, okay, that means that we will be able to say that your HN, okay, is 0 for negative values of n. Okay. We will be able to modify, okay, or we will be able to modify the convolution formula by actually changing the lower limit. Okay. So if if your HN, okay, if this is actually causal, or if this is actually if your HK, okay, here is 0 for negative values of N, I mean K, okay, then obviously the contributions of the product sequence for negative values of K is 0. So that is why we can actually start our summation, okay, or we can start forming our product sequence when K is equal to 0 up to infinity, okay. Or otherwise, if we opt to place the impulse response to be the one that is time folded and shifted, okay, then when you actually fold this sequence, okay, when hn is 0 for n is less than or equal to 0, and you substitute it inside the convolution formula, okay, then h of negative k, okay, is actually 0 for for positive values of k, okay, kasi magta-time fold nga siya, okay. So kapag nag-time fold siya, kung causal yung system niyo, it's a right-sided sequence. But when you time fold it, okay, when you reverse it in time, it becomes 0 for positive values of k. Okay? So that when you actually shift this, okay, your hk is non-zero for negative values of k until the amount of shift. Okay? Until where the shift of the convolution is. Okay? So that is how the causality condition actually modifies your convolution formula. Okay? So it is sometimes convenient to call a sequence that is 0 for n less than or equal for n less than 0 a causal sequence. Okay, ito yung pinag-usapan natin dun sa figure kanina. Okay, or a right-sided sequence. Okay, a sequence that is 0 for positive values of n as an anti-causal sequence, okay, or a left-sided sequence, and the one that is 0 for both positive for negative and positive values of k, n, I mean, a non-causal sequence or a two-sided sequence. Okay, so since the impulse response Hn of an LTI system can be considered as a sequence, okay, the causality condition implies the following statements. Number one, a system with right-sided Hn is a causal system. This is sabi ko, if these sequences actually pertain to Hn, okay, then we can apply these statements. Okay, so a system with right-sided Hn, okay, is a causal system, while a system with left-sided Hn, okay, is an anti-causal system. Okay, and finally, a system with two-sided Hn is a non-causal system. Okay, so as indicated previously, causality is required in any real-time signal processing application. Okay, since we can only implement your real-time signal processing tasks, okay, when your system is actually causal. Okay, at any given time, okay, we have no access to the future values of the input signals since we are talking about a real-time signal processing. So we don't really have an idea of what the future values of your input sequence are. Okay, only the present and past values of the input signal are available in computing the present output. We may know in advance the entire Hn. Okay, we may know in advance the entire Hn because that characterizes our system. Okay, but our problem is the input. Okay, being arbitrary and being generated in real time. Okay, we don't really have an idea of what the future values of your future value. What would be the future value of your input signal is. Okay. So now, so earlier we have modified your no your convolution formula, um, considering that your HN or your impulse response is causal. So we have seen it here in your equation 10. Okay. Now, in equation 11, it actually modifies the convolution formula, uh, provided that your system is causal. Okay. And the input is a causal sequence also. So causal yung ano nyo, causal yung HN niyo, and at the same time, um, yung input sequence niyo is also causal. So as you can see, the limits are the same in both cases. Okay? And that is because, for example, in this case, um, again, here, if your HK is causal, then it modifies now your lower limit to 0. Okay? And if we opt to have your input, okay, to be time reversed and shifted, okay, then the product sequence would be 0. Okay? For I mean this one. Okay, sorry. Your input sequence, okay, your input sequence, okay, would be 0, okay, for k uh, greater than n. Okay? Magsi-zero 'yan pagka kasi tinimefold mo siya, eh, tapos shift mo siya. Okay? So since naka-timefold siya, okay, since your xn is time-folded, okay, because of negative k here, okay, then it becomes 0 for positive values of k. Okay? And then if you shift it, okay, if you shift the time folded input sequence, um yung sequence nyo, okay, would be non-zero until dun sa shift nung natin. Okay? If you're having difficulty understanding this, recall na I had an illustration about this on lesson 3.1. Okay? This one. If you can remember this is under example 3. Okay? Example 3 ng lesson 3.1. Okay? So this illustrates u of n minus k. Okay? U of n minus k, wherein your u of n or u of k is time folded first and then shifted by a certain number of samples. So as you can see, it is 0 for your sequence is 0 for time index that is greater than that amount of shift, which in this case is 6. Okay. So there. So as you can see, your x of n minus k, okay, is 0 for k greater than n. So therefore, from n plus 1 up to infinity, this product sequence will also become 0. Okay, so therefore we can set the limits from k equals 0 up to m. You can actually verify this with example 3 also of lesson 3.1, wherein we have evaluated the output sequence y of n when your xn is something like 1/2 raised to n u of n. Okay, nhn is 1/4 raised to n u of n. Kung tama yung pagkakalala ko ng problem na yun. Okay? Notice that both of them are causal. Okay? Now notice that at one point of the example, we've been able to change the limits of your summation of your convolution summation. Okay? From k equals 0 up to n. Okay? Again, owing to the fact that this sequence, okay, or this u of n, this u of k, okay, is when you substitute it here, it becomes u of k. That u of k becomes 0 for negative values of k. Okay, while if this is the one that is time reversed and shifted, it becomes 0 for k greater than n, so that we were able to change the limits from 0 to n. Okay. That's example 3.1 nga. I mean example 3 of lesson 3.1. Okay. So there. Now, even so, if we actually had, instead of having your input sequence be time reversed, and shifted, if it is the HN, that is time reversed and shifted, okay, ganun din, okay. This one, okay, becomes 0. Your x of k becomes 0 for positive, for negative k, so that the lower limit becomes 0. Okay, while this one, okay, is your h of n minus k is 0 for k greater than n. Okay, so the upper limit becomes n. Okay, so let's take a look at example 5 now. So determine the unit step response, okay, of the linear time invariant system with impulse response h of n equals a raised to n u of n with the absolute value of a, okay, or the magnitude of a if a is complex, okay, is less than 1. Okay, so we will not really qualify this to be a real or a complex sequence. Okay? So, pagka wala sinabi kung siya ay real or complex sequence, this one just simply tells us, this condition simply tells us that the magnitude of A, okay, whether it's real, okay, purely real, okay, or complex, okay, its magnitude is less than 1. Okay, now, ano yung tawag na unit step response? Okay, again, this is response. So response is output. Okay, so always remember that response is pertains or always it always refer to output sequence. Okay, now unit step response, okay, is the output sequence for a unit step signal. For a unit step sequence, okay, input. Okay, so pag sinabi nyo unit step response, okay, you are looking for the output sequence, okay, where the input is a unit step sequence. Okay, so yun yung tawag natin unit step response. So ito yun, the input to the system is a unit step signal, dahil nga unit step response ang hinahanap natin. Okay, so that is your x of n is u of n. Okay, so we note that our system is a causal signal or a causal sequence. Okay, now the sequence or the system, okay, has a decaying exponential as its impulse response. Okay, so we are sure that this is a decaying sequence, or this sequence will eventually become 0 as your n approaches a large value. Okay, simply because of this condition. Okay, so alam natin yan. We're sure of that, okay, because of that condition. Now, because the exponential factor, a raised to n, is multiplied to a unit step sequence u of n, okay, we see that your impulse response is 0 for negative values of n. Okay, so dahil naka-multiply, okay, because we have multiplied your exponential sequence to a unit step sequence, that would make now your hn, okay, that makes now your hn to be a causal sequence. Okay, and that would imply, okay, that would also imply that the linear time invariant system represented by this impulse response is a causal system. Okay, that would be the implication. Okay, so meron kang causal input sequence to a causal system. Yun yung situation natin dito sa example 5. Okay, now since both the input signal or the input sequence and the system's impulse response are causal sequences, okay, ito yung pinag-uusapan natin dito sa equation 11 ninyo. Okay? Both the input, okay? Both the input and the system, the input is a causal sequence. The system is a causal LTI system. Okay? So, we can use any of these two kung ganun yung situation natin. Kung causal yung LTI system natin at yung sequence natin at yung input sequence natin is also causal. So, since it would be since our input sequences, okay, our input sequence is u of n, and that our impulse response is a raised to n u of n. It seems na mas madaling i-timefold. It would be easier to timefold and shift yung xn kesa sa hn because hn is carries a much more complicated form kesa sa xn. So we use this. Okay, si xn ang i-time fold and shift natin. Okay, so after substitution, we will have we will simply have this as we will simply have this after substitution, we will simply have this as y of n equals the summation of yung hk natin is a raised to k. Okay? And again, since naiba na natin yung limits yung lower limit natin, we will not need to write this because it is 1, okay, within this interval. For k equals 0 up to n, your u of k is 1. Okay? And this one, okay, within this interval, okay, is also 1. Okay? So, this is a raised to k times 1 times 1. So, yan na lang talaga yung may iwan. So, from k equals 0 up to n. Okay? So, ito na lang yung magiging expression natin after substitution. Again, considering that your system is a causal LTI system and that your input signal or input sequence is a causal sequence. Okay? So as we can see, this is a finite geometric sequence. Okay? This is a finite geometric sequence. So sum, again, is given in Formula 8 of lesson 2.1. So napaka-importante talaga ng formula na to. We have been using this for three times now, siguro. Okay, at least 3 or 4 times. Okay, in 2 different topics pa. Okay, we have used this to compute for energy and power. We are also using this for this one. Okay, so since your A is not equal to 1, okay, your A here is not equal to 1, okay, we will have the first, this one as its sum, okay. So we now consider, or we now have your y of n equals 1 minus a raised to n plus 1 over 1 minus a, okay, for n greater than or equal to 0. And it is 0. Remember that your y of n becomes 0. Okay, for n less than 0. Again, it is because, okay, ang logic dito, okay, being your y of n 0, your output sequence being 0 for negative values of n is that your input sequence, okay, is actually is a causal sequence, and your system is a causal LTI system. So in this case, pagka ganyan yung situation natin, the tendency is that your output sequence also becomes a causal sequence itself. Okay, pati yung output sequence natin nagiging causal. Okay. So that's causality. Okay, now let's talk about stability. Okay, as indicated previously, okay, stability is an important property, okay, that must be considered in any practical implementation of a system. Okay, again, you need your system to be stable. Okay? Because a system that is unstable would lead to output sequences that has a very high value. Okay? And kung ito ay if this is algorithm lang, if this is purely algorithm, or if you're talking about systems that are purely algorithm, okay, at yung output sequence nyo naman nasa computer nyo lang, and there's really no voltages or currents involved. Okay lang siya kasi that would just uh, cram up your memory. Okay? Pupunuin niya lang yung memory niyo with a lot of values. Okay? So a simple restart of your computer would suffice. Okay? Pero if there are voltages and currents involved na, okay, stability is needed because of safety reasons. Okay? Dahil kapag we're talking about unstable system producing infinite amplitudes of voltage, medyo delikado yun. Okay? So, in the previous topic, okay, we have used the Bibo stability, okay, to identify whether a system is stable or not. Bibo, again, stands for bounded input, bounded output. Okay? Ibig sabihin, okay, if you have for a system, okay, for a system that is fed, okay, by an input sequence that is bounded. When you say a sequence is bounded, it means that your input sequence, okay, eventually becomes zero as your n, whether positive or whether on the positive side or on the negative side, becomes very large. Okay? So that's an indicator that your xn is bounded. Okay? So one thing that we are looking at here is that the energy of these sequences, okay, should be finite. Okay? Or at least meron siyang finite average power if xn is say for example periodic or non-ending. Okay? So bounded siya. Okay? So that's one, no? Ito yung isang pwede rin naman your xn approaches a certain constant number. Okay? As your n approaches infinity. So sorry, medyo napag-mix natin. Okay. So kapag ganito kasi, if your xn approaches 0 as your n approaches infinity, then your xn or your input sequence is an energy signal. So ito yung magiging condition natin. While if your xn approaches some positive some finite value, finite non-zero value as your n approaches infinity, then it is a power signal. Okay, because your sequence persists over time. Okay, so it's a power signal. Okay. So dapat meron siyang finite average power. Okay, so ito yung condition natin. So that is how you would be able to say that your input sequence is bounded. Okay. Now, if you have if you have fed your system with a bounded input sequence, supposedly dapat yung mapoproduce niyang output sequence is also bounded. Hence the name bounded input, bounded output. Okay? So yan yung Bibo stability as was discussed dun sa lesson 2.4. Okay? Now, we will use now your impulse sequence, okay? Oh yeah, your impulse response to be able to determine whether a system is stable or not. Okay? So again, in light of the new information that is h of n, we will be using that, okay, in order to characterize the stability of the system. Now, in terms of h of n, a sufficient and necessary Again, sufficient siya. Ibig sabihin, okay na siya as it is. Okay? But necessary. Ibig sabihin, kailangan. Okay? A sufficient and necessary condition to ensure the stability of the system is that its impulse response is absolutely summable. Okay? So, which means the terms of your, when you add the terms of your h of n, okay, it will produce uh, a finite sum. Okay? So, pag sinabi nyo absolutely summable, okay, absolutely summable, it means that adding, adding the terms, adding that terms of the sequence, okay, produces a finite sum. So pag inad natin lahat ng terms nung hn natin, it becomes finite. Okay? So that is the way that we determine whether a system is stable or not using your impulse response. Okay? So this condition, okay, this condition also implies that for a system to be stable, okay, for a system to be stable, its impulse response hn goes to 0, okay, as n approaches infinity. Okay? The only way na magiging absolutely summable, okay, yung hn ninyo, is that the terms of your hn, okay, becomes 0 as your n, whether on the positive or on the negative side, becomes 0. Okay? So, actually, ito yun. Itutukoy natin doon sa part na yun. Okay? So, if your hn, lalagay din natin siya dito. If your hn, okay, approaches 0 as n approaches infinity, plus or minus, okay, we will be considering that your hn is absolutely summable. Okay? And that it points to a system represented by absolutely summable hn is stable. Okay? It also points out that it also implies that your hn is a sequence, or is an energy sequence. Okay? It would imply, dahil nga dito sa condition na to, it would imply that your n should be an energy sequence. Okay? So, yun yung natin dito. Stand natin dito. Okay? So, if your hn is actually an energy sequence, okay, we can say that your system is stable. So, let's take a look at example 6. Okay? So, let's analyze the causality and stability of the systems characterized by these two sequences. No? Okay? Now, in terms of causality, it would be very easy for us to identify that both systems are causal. Okay? Mainly because since both sequences, okay, have u of n, or unit step signal or unit step sequence as factors, okay, then it is easy to say that both of these, okay, are 0, okay, for negative values of n. So it's really easy to tell. The causality from there can be easily concluded, okay, because of these factors. Okay, so the unit step sequence as a factor in both sequences makes these sequences satisfy the causality condition in equation 9. Okay, so if you actually generate the terms of the impulse response sequence for this interval, okay, you would be seeing, okay, So this is for negative values of n, while this is for positive values of n. So it is very clear, okay, that both your hn, h1, and h2 are 0 for negative values of n, while they are non-zero for positive values of, for 0 and positive values of n. So, ang conclusion natin is that your h1 and h2, both of them are causal, LTI systems. That's our conclusion. Okay? Now, talking about stability, no? Okay. So, in terms of stability, your H1 is is the sequence 1.2 raised to n u of n. So we see that the sequence is an increasing exponential sequence. Okay? Mainly because this is an exponential sequence of the form a raised to n u of n. Okay? And that your a, or the magnitude of your a, is greater than 1. So therefore, yung ano nyo, yung exponential sequence nyo is increasing. Okay? Remember that if this is instead less than 1, you have a decaying or decreasing exponential sequence. So here, you have here 1.2 raised to n, u of n, okay, as an increasing exponential sequence. Now, if we actually attempt to evaluate this sum, again, this is the condition for absolute summability of a sequence. That is, we will attempt to add the terms of your sequence. Okay, and knowing the fact that your h1 is causal, so sisimulan natin yung summation niya when k is 0. Okay, so if you evaluate that sum, we will be able to form this sequence. This series. Okay, and notice that this is an infinite geometric series. Infinite yan kasi the upper limit of your summation is infinite. So this is an infinite geometric series. Okay? And as we know, we don't have a sum. Okay? We don't have a sum for infinite geometric series. Okay? When the common ratio of the geometric series is greater than 1. Okay? So therefore, h1 is not absolutely summable. Okay? It is not absolutely summable. And therefore, the system represented, this is our conclusion for h1. The system represented by h1 is considered to be unstable. So, yan yung conclusion natin. Okay? So, the system represented by h1 to be unstable. Okay? So, we will be able to see na kapag kinumpute nyo yung partial sum nito, okay, as we have learned in a previous course, we will see that partial sum actually does not approach a certain value. So therefore, the series is a divergent series. Okay? So using MATLAB for that, okay, ito yun. Okay? We find, for example, the partial sum, okay, for k from 0 to 10, and then for k from 0 to 20. So parang ito yung first 11 terms of your h1, first 21 terms, and so on. You see that the partial sum actually does not approach a certain value. Okay? And ang rule, ang rule natin for infinite geometric series, for infinite series, okay, that the rule is that if the partial sum of an infinite series, okay, does not approach a finite value, okay, then the series is divergent. Okay, and if the series is divergent, it means that the sum okay, the sum of the terms of the sequence as we increase the number of terms is approaching infinity. Okay, so that means that your H1n again is not absolutely summable. Okay, so again, it points to the fact, it points to the to uh, an evidence that your H1 is not stable. Okay. Um, Now let's talk about H2n. Okay. Again, H2n is given as 0.4 raised to n Q of n. Okay. Which we expect that the sequence is a decaying exponential. So we know here that H2 approaches 0 as your n approaches infinity. Okay. So if we actually evaluate the sum, this sum, okay, if we actually evaluate the sum, so that if we want to see the condition of absolute summability, okay, we can actually add, or we can actually find a finite value for your infinite geometric series. Okay, again, recall na we have a sum, the sum of an infinite geometric series, okay, of the sum of infinite geometric series when when the common ratio is less than 1, okay, is equal to 1 over 1 minus 8. So we have been able to study this on a previous on a previous course and on a previous topic. Okay? Sa lesson 2.1. Okay? Naka-indicate itong sum na to. Okay? So we have this as your sum of the infinite geometric series. Okay? Given that your A, or the magnitude of your A is less than 1. So since A is 0.4 here, okay, we will be able to evaluate the sum to 5 over 3. So therefore, yung the sum of the terms of H2 is 5 over 3, a finite uh, a finite number. Okay? Thus, it indicates na satisfied yung ating stability condition. Okay? Now, if you actually use MATLAB, okay, these commands, okay, and again, do or evaluate, okay, evaluate the partial sums of your H2, okay, of the terms of your H2 as we increase the number of terms. Okay, first thing that you would be able to see here is that yung value ng H2n nyo as you increase K, okay, is actually approaching 0. And as you can see, the partial sum is actually approaching a certain value, which is ito nga yung 5 over 3. Okay? So, in that case, ang rule natin dito, okay, if if the partial sum of an infinite series approaches a finite value, okay, your infinite series converges. It converges. Okay, so therefore, yung magiging sum or yung the value at which this partial sum converges to is the sum of the sequence. I mean the sum of the series. Okay, so again, we conclude that that sum is 5 over 3. Okay, so this is consistent also. Itong again this 1.66667 actually kasi 4 decimal digits lang yung ni-report ni MATLAB, but it actually points to 5 over 3. Okay. So as you increase your K, the number of the terms that you are trying to add, your sum approaches 5/3. Okay, which is consistent with what we have obtained using the infinite geometric series formula. Okay. So again, as we have concluded in the analytic solution before, your stability condition is satisfied, and therefore we can just conclude that your H2 is stable. Okay. You can also take a look at the plots of H1 and H2. as a sequence. Okay, and see that again H1 is an increasing exponential. Okay, while H2 is a decreasing exponential. Okay? So therefore from there makukuha niyo yung ano niya, makakakuha tayo ng clue about the system's stability. But again, don't be deceived kung ito hanggang dito lang yung ano, or limited lang yung number of terms na yun. Kasi baka mamaya, nandiyan siya tapos mag-approach na pala siya ng certain finite value. So, that's not ano. Okay? That's different from talagang increasing. Okay? So, be careful with those interpretations. Okay? Also, as we can see here, that the values of your sequence are 0 for negative values of n. Okay? So, kita natin yan dyan sa ating plots. So, we see that both systems are causal. Okay? And then H1 is an increasing sequence, H2 is a decreasing sequence. So therefore, we see that H1 is unstable, okay, and H2 is stable. Okay, so there. Now, you can also take a look at this script, no? Okay, take a look at this script, which is provided to you from the link on your to see how the step response becomes off for H1 and H2. Okay, taking note that H1 is unstable and H2 is stable. Okay, so we have used yung last part nung script na to uses or use numerical convolution in order to determine the step response, okay, of these two systems. Okay, and we see we will be able to generate the following plot. This is for H1. So as you can see, the step response actually becomes very large. Okay, as your n approaches, as your n increases. Okay, as your time index increases. While for H2, which is again classified as stable, the step response actually approaches a certain finite value. Step response to ibig sabihin, ito na yung output ng system niyo on a given input, in which case the input is actually unit step sequence. Okay, so unit step sequence is bounded. Okay, bounded siya because it approaches a certain finite constant value, okay, as your n increases. So we can consider that to be bounded under this condition. Okay, under the condition na sinulat natin dito, layo na pala ito. Under the condition dito na your x of n is approaches a certain constant finite value as your n approaches infinity. Okay, so that is that is how we characterize your u of n. One example of a sequence that approaches a constant finite value as n approaches infinity is a u of n, the unit step sequence. Okay, and if we actually use that as an input, okay, to your system, ito yung lalabas. So kung ang natin, if our criteria for determining stability is bounded input, bounded output, as you can see, pagdating mo dito sa part na to, tumataas na yung values ng output sequence natin. So therefore, your bounded input does not or is not able to give off a bounded output for H1 or for system represented by H1. That is why we say that H1 is not Bibo stable. Kasi bounded yung input mo eh. Your input is bounded. Okay? U of n siya eh. So it's a bounded input. But the output is not bounded. Okay? The output becomes very large at a certain point in time. So therefore, hindi siya Bibo stable. And in general, hindi talaga stable yung H1 niyo. While for H2, okay, as you can see, for your H2, we see that nag-approach siya ng certain constant value. Yung output natin, this is the output. Okay, yung output natin approaches a certain constant value given that your input is also approaches a certain constant value. So bounded yung input mo, bounded din tong output mo. So we say that H or system represented by H2 is a is BIBO stable. Okay, so yung system na represented ng system na H2, impulse response na H2 is BIBO stable. So, yun. Okay, so in terms ng graph, ma-determine natin yung BIBO stability. Okay? And again, the example 6 actually provided you with the way on how to actually determine the stability of the system using your impulse response. Now, we have here new characteristics, okay? New characteristics of your LTI system. Okay, ito yung sinasabi ko sa inyo ng mga characteristics that are now really exclusive to LTI systems. Okay, so we characterize your system as either having a finite duration impulse response or infinite duration impulse response. Okay, so LTI system, okay, LTI system can be classified in terms of the length of your impulse response Hn. Either it is finite yung length niya or yung duration niya, okay, o kaya infinite siya. Okay, and formally, we call systems, okay, we call systems having finite duration impulse response as FIR systems. Okay? Finite impulse response yung FIR. Okay? And we call systems having infinite duration impulse response as IIR systems. Okay? So, pag finite yung length of the impulse response, we call it as an FIR system. Okay? Otherwise, we will, if the length of the impulse response is infinite, then we will consider that to be an IIR system. Okay, so that's new characterization, okay, of your impulse response. Okay, now, a causal FIR system, okay, a causal FIR system has an impulse response that is zero outside of some finite time interval. Again, take note na finite yung length ng ano ninyo, ng impulse response ninyo. So if you have an FIR system, okay, yung h of n ninyo, okay, is a sequence, okay, having finite non-zero terms, okay, having finite non-zero terms. Okay? And if you actually consider this to be causal, okay, in addition na siya ay FIR, yung Hn ninyo is also causal, then yung first term dito of your sequence actually starts when n equals 0. Kasi causal siya. Okay? So at some point here, okay, yung last term ninyo, n equals big N, for example. So, yan lang yung ano, it means that your Hn, okay, your Hn is 0 for n less than 0 and n greater than n, big N. Okay? So, non-zero lang siya within a certain time interval. Okay, so yun. So, that indicates or that points to a system having a finite memory, okay, of length m samples. So, ibig sabihin yung haba or yung number of terms dito, okay, the number of terms here. Actually, I use m here, no? Pero m pala yung ginamit niya. So, the length here is m, which is actually n plus 1 dun sa una kong ginamit na, na numbering system. Okay? Na counting ng number of terms. So, the length of this Hn is actually m, which is n plus 1 if it starts from 0 and ends with n. Okay? So, yun yung number of terms ng Hn. Okay? Now, since you are using, okay, or your Hn has now has now a finite number of terms. Okay? The system also has a finite amount of memory. Okay? Because it only needs to store finite amount of terms para ma-save niya yung values no h of n natin. Okay? So now, if your system is causal, okay? If your system is causal and also FIR, okay? And also it is FIR, okay? The convolution formula reduces to into this formula. Okay? Again, yung HK niyo, okay, will only be defined for K between 0 up to M minus 1. Kasi nga length M eh. Okay? Kung length M siya, it means na sige, baguhin ko tong numbering system ko dito. No? So kung length M siya, okay, the first term, okay, kung causal the first term would be located when n at n equals 0 or would be indexed at n equals 0. Yung last term yan, okay, would be indexed as m minus 1. Yan. Okay, so itama natin siya dito. Okay. So in this case, if the first term is at n equals 0 while the last term of your hn, again, dahil nga finite siya, okay, is at m minus 1, okay, the number of terms or the number of elements of your hn is m. Okay, so ito yung length na tinatawag ng this is the length. Okay, and we can say that h of n is 0 for n less than 0 and n greater than m minus 1. So kung ito yung case, that automatically yung hk dito, that automatically changes both the limits, okay, of this summation dito. Okay? Mag-change kagad yung ito lang yung hk lang regardless of what x of n is. Okay? With just hk, if hk is causal FIR system, automatic yan na pag sinubstitute nyo dito si hk, yung limits nyo mag-change kagad from 0 to n minus 1. Okay? So, a useful interpretation of this expression is obtained by observing that the output at any time n is simply a weighted linear combination of the input signal samples xn minus 1 up to xn minus m plus 1. Okay? So, ang sinasabi niya dito is this. The output is actually weighted linear combination. Pag sinabi yung weighted linear combination, yung product sequence ninyo, okay, the input sequence, okay, is being scaled. Okay? Yung xn ninyo, okay, is scaled by a vector of weights. Kung maalala nyo, pag sinabi yung weighted, say for example, weighted average. Okay? Like for example, yung pagko-compute ng general weighted average niyo, GWA. Okay? You use the number of the units of your course. Okay? And multiply it with your grade for that particular course. For example, if a course has 3 units, okay, and the grade that you obtain there is 4.0, okay, then the weighted your weighted grade for that particular course is 12. Okay? So ngayon, kapag pinagsama-sama niyo yan, actually, say for example, another 3 unit course na nakuha niyo 3.5 and so on. Yung makukuha yung product dito, pag in-add nyo yan, ang tawag doon ay weighted linear combination. This is called the weighted linear combination. So, ganun din siya dito. Okay? Say, for example, this is your xn. Okay? This is your xn. Okay? And your xn, okay, the input sequence, okay, is being scaled by a vector of weights. Ito nga yung tinatawag yung vector of weights. Okay? And that vector of weights is actually your Hn. Okay? That vector of weights is your is your Hn. Ngayon, ang pagkakaiba lang with that, with the example that I had at saka ito, is that your Hn is actually moving in time. Okay? You are actually moving your Xn, I mean your Hn in time. Paano moving? Okay? Say for example, this is your Xn. Okay? So, ito siya, for example. Okay? Kung maalala niyo, kung if you are able to to remember that your convolution algorithm requires you for your Hn to be shifted. Okay? Or say wait lang. Sorry. In this case pala Xn ang i-shift natin. Okay? So ibig sabihin naka-fix is Hn. Okay? Wait lang. Yan. Hn. Okay? Now, if you remember, dun sa algorithm natin nung convolution is that one of the sequences should be shifted. Okay? So as you can remember, yung Xn natin is actually being moved in time para makakuha tayo ng product sequence. So as you progress in time, minumove natin si Xn. Okay? We are shifting or moving your Xn in time. And then from here, we will be able to generate, okay? In each of this case, we will be able to generate a certain product sequence. Tapos makukuha natin yung value ng ating y of n by adding those product sequence. So when n is something, okay? When n is n1, okay? So we will be able to get y of n1 here. So this is when the shift is n2. Okay? By the way, these are xn. And as you can see, your xn, this is x of negative n. Time-folded na yung xn natin. Okay? So this is x of negative n. Sorry. X of negative n. Time-folded siya. And then we are shifting it with a certain amount of shift. Okay? So here, the shift here is, say for example, n1. Bubuo tayo ng product sequence between hn at saka x of negative n with this shift. Okay? We will be able to compute for y of n1. Same thing here, bubuo tayo ng product sequence between hn and x of negative n shifted by n2. So the sum of the terms of the product sequence would be y of n2 and so on. So ma-generate natin si y of n here. Okay? So that's how we generate the output sequence using the convolution sum. Again, yung product sequence natin is the weighted linear combination. Okay, the product sequence that we are seeing is the weighted linear combination. Okay, so xn, okay, is scaled. Ini-scale natin si xn by a vector of weights. And that vector of weights is again your hn. Okay, tapos we are moving xn. Okay, we are moving xn in time by shifting. So by shifting. So by shifting your xn, makakabuo tayo ng weighted linear combination of xn and hn by multiplying it. Okay? So after which, isa-sum up natin siya, coming up with a term for your output sequence. So that is so yun nga if you actually attempt to expand the sequence, the convolution formula for a certain amount of shift for n equals 0, n equals 1, n equals 2, n equals 3, you would be able to generate this. Yan yung tinatawag yung weighted linear combination. Okay, that is what we call the weighted linear combination. Okay, yung h0, x0, h1, x negative 1, and up to this those are the terms of your product sequence. Pag inad nyo lahat ng terms ng product sequence na yon, you now have your weighted linear combination. Okay? At ano yung weight niyo? yung weight ninyo itong xn. These are the weights. Okay? So you do that for all n's. Okay? So that you can generate all values of your output sequence. So first observe that in all of these expansions, the number of terms is to be added is always m. So we see or we observe na lahat ng number of terms for each of this are all m's. And that is simply because yung limits nyo kasi. Okay? Yung limits nyo is simply simply indicates na you have m number of terms to add or m number of m number of terms of the product sequence that you will be able to add. Okay? For all yan, for all n's. Okay? So, the number of terms to be added is always m. The number of the terms of the impulse response sequence, okay, is also m. Okay? And the number of input signal samples involved, okay, from x0, for example, up to x of negative m minus plus 1 is also m. So, ibig sabihin, in these statements or in these statements na ginawa natin from that observation, if Hn is causal FIR system, okay, of length m, what we do is actually scale m number of m number of terms of your input sequence of xn, your input sequence, by hn. So we will only involve at any given time that we are attempting to compute. Okay, we are attempting to compute at any given time. I-involve lang natin yung m number of terms of xn, regardless of how long your xn is. Ang may involve lang lagi sa kanya is m number of terms. Okay? So, yung m number of terms na yun lang lagi yung i-ano natin. I-involve natin. Okay? So, that. So, second, observe that while the terms of the sequence, okay, so while the terms of the sequence Hn is always involved in the determination of the output for all n's, okay, the terms of the sequence Hn involved, okay, will be always the present term. Lagi kayo magsisimula. Pag magko-compute kayo with, if you have to compute the output of a causal FIR system, you always start with the present term. Tingnan nyo lagi to. Tingnan nyo to. If you have to compute y0, you would start with x0. That's the present term. These are the past terms, x of negative 1 up to here. Those are past terms. Okay? So, you will only start, or you would involve the present term and the past, the present input and the past inputs. Okay? Kapag nagko-compute na tayo ng y of 1, okay, we will start with x of 1 and then the past terms or the past inputs, the past values of your inputs. Okay? If you're computing for y of 2, okay, we will start with the present x of 2. Okay? And then involve the past values of your input and so on. Okay? So it will always involve the present term xn and it's m minus 1 past terms. So bakit m minus 1? Again, ito yung isa. Then m minus 1 terms for a total of m number of terms. So, ayun. Ito yung explain nito sa second observation niya. Okay? So, in all of these steps, the computation of the output involves only m number of input signal values. Okay? The present input signal value and m minus 1 input signal values that came before it. Okay? Now, the m terms of the impulse response, impulse response sequence Hn, okay, scales each of these m input signal values. So each of those input signal values is being scaled, okay, or being weighted by your h of n. So we refer to this since finite yung ano nyo, no? Finite yung hn nyo. We refer to this as a window. Okay, sa signal processing in signal processing lingo, okay. A sequence, okay, that is of finite length, okay, is called a window. Okay, tawag natin doon window. Rectangular window usually. Okay. So the window being referred to in the discussion is the M input signal terms involved in the output computation. Okay. So observe that while the window maintains its length at M, okay, the values inside this window shifts, okay, as the output computation progresses in N. Ito ngayon. Okay. While we maintain na yung length nito ay M, okay, also the length of this is are all M kasi M number of terms ang i-involve natin. But again, starting with the present term, okay, the first term here would always be the present term, okay. So all of them have length M, okay. So while we maintain that the length of the window is still M, ito M din ito, okay, we see that inside this window, nag-shift yung values ninyo. Okay, nagbabago siya. Dahil nga, the convolution calls for shifting as one of its steps. Okay? So starting with the present input, signal value xn and dropping or forgetting the m-1. So once na magamit nyo na yung isang part ng xm ninyo or xn ninyo, kakalimutan na natin whatever the value of xn outside the length of the window, we will drop or forget, okay, m+1 input signal values, okay, after shifting the values inside the window. Okay, so in that case, we need to drop them or we need to forget them kasi nga tatandaan nyo, if your system has a memory of length m, because the length of the hn is of length m, then yun lang yung kaya niyang i-store. So therefore, it will also provide a memory space for m number of xn. Okay? So therefore, values of xn outside of that m number of values is forgotten or is dropped. Okay? So, dun natin nakuha that FIR system has a finite memory of length m samples. Okay? So, there. Now, a causal IIR system, again, IIR stands for infinite impulse response, infinite duration impulse response. Okay? So, it has an impulse response that is 0 for negative values of m because it is causal. And in contrast to FIR system, IIR systems have infinite amount of memory because the length of the impulse response is infinite. Okay. Now, in contrast to FIR system, okay, the output of a causal IIR system would be based on the convolution formula, whose limits are from 0 to infinity. Okay, again, yung causality ng system niyo would force the lower limit to become 0. Okay, but since we don't know, this is arbitrary, so we don't know really the length of xn, but we are sure that x of k, okay, is infinite length. So therefore, the convolution sum would require that we have to sum up infinite terms of your product sequence. Okay, so since hn would be of infinite length, the computation of the output always involves infinite number of input signal values. And this will require an infinite amount of memory, okay, to save all the input signal values from the present xn up to the very first one, which is your x of negative infinity. Okay. So tulad nung sa FIR system, we will maintain here a certain window for you to be able to scale your input. But the thing is that the length of that window, instead of finite as in M, katulad ng previous discussion natin, it becomes infinite. So we will have to maintain an infinite length window. Okay? Which is actually impractical. Okay? Which is actually impractical in practice. Basically because we don't have that much resource to have or to design a system that has infinite amount of memory. Okay? But we will be able to show in a later topic the practical implementation of IIR system, okay, can be okay, can be made so that it would only involve finite amount of memory. Okay? So, malalaman natin later on that if your system is an IIR system, instead of actually implementing the system as it is, okay, we will be able to write alternative ways uh, in order to implement it, okay, and then we will be just using finite amount of memory, okay. So we will be characterizing FIR and IIR systems in more details, okay, in future topics. Okay, so that ends our discussion on lesson 3.2.